Alright, for lesson 19, this is called the Remainder Theorem, and our objective for this is we're going to be able to determine factors of a polynomial function by using the Remainder Theorem. So we still have to get into what the Remainder Theorem is in the first place. So just some opening thoughts to wake up our brain. Is 6 a factor of 36? Yes, okay, because it divides evenly with no remainders. 5 is not a factor of 36 because it doesn't divide evenly. It's 36 divided by 5 is 7 with a remainder of 1. Another thing you can think about is if you rewrote 39 as 7 times 5. Oops, I gotta turn my pen on. Okay, 7 times 5 is 35 with a remainder of 4. 41 is 4 times 10 with a remainder of 1. So the second question on here, or the second part on here, is 3 a solution of x squared minus x minus 6? Well, a solution means that when x equals 3, that polynomial will equal 0. So let's plug it in. So our first method, we're just going to plug in 3 wherever we see x and see if it equals 0. So we have 9 minus 3 is 6, minus 6 equals 0. Yep, okay, so that one worked. The other way is we can factor x squared minus x minus 6. We can break it down into x minus 3 times x plus 2. And I noticed that for x minus 3, when x equals, if x minus 3 equals 0, then x would equal 3. So if 3 is a solution, then the binomial x minus 3 is a factor of x squared minus x minus 6. Okay, let's keep moving on. So we're just kind of building that knowledge. It's okay if you feel a little bit confused right now. Stay with it. It's going to keep building on itself, and you'll get there. So we're going to talk about discovering the remainder theorem. So the first thing is determine if x minus 2 is a factor of f of x equals 3x plus 8x minus 4. So it first says divide by x minus 2. So I'm going to use the reverse tabular method. And I know I end up with at the end 3x squared plus 8x minus 4. And I'm dividing by x minus 2. So now when we divide, it's really important we always start in the top left corner. So I have to end up with 3x squared here. So I must have multiplied my x by 3x. Now I go 3x times negative 2 is negative 6x. But I need a total of positive 8x when I'm all done, so this has to be a 14x. So plus 14, 14 times negative 2 is negative 28. So now the question is, how do I get from negative 28 to negative 4? What do I have to add on to that to get there? And that is a remainder of 24. Negative 28 plus 24 is negative 4. I can also find f of 2. So if I do 3 times 2 squared plus 8 times 2 minus 4, so I get 3 times 4 plus 16 minus 4. So I get 12 plus 16 minus 4. I get 28 minus 4 is a remainder of 24. Okay. Actually, I don't want to say remainder there. I lied. Just say equals 24. Okay. Let's go on to the next one. Oops. It was already on that page. Okay. Not a lot of room here. So the next one is determine if x plus 1 is a factor of g of x equals x cubed minus 3x squared plus 6x plus 8. So a couple ways you can do this. You can do the tabular method or you can use long division, whatever you're most comfortable with. So I'll just do the tabular method. I know I end up with x cubed minus 3x squared plus 6x plus 8. And I'm dividing by x plus 1. So x cubed, so that becomes an x squared, positive 1x squared, so I have to add a negative 4x squared to get my total of negative 3x squared, minus 4x. Negative 4x times 1 is negative 4x. I'm at negative 4x. I need to get to positive 6x, so I need another 10x plus 10. 10 times 1 is 10. So how do I get from 10 down to 8? I have a remainder of negative 2. 10 plus negative 2 equals 8. Also, if I find f of negative 1, so hang on really quick, I just wanted to put on here those things. F of negative 1 equals negative 1 cubed minus 3 times negative 1 squared plus 6 times negative 1 plus 8. So that's going to be negative 1 minus 3 times 1 is negative 3 minus 6 plus 8, and that's going to be negative 2. Okay, so we're starting to discover this remainder theorem. So if you notice, when you factor a polynomial by a binomial, if there's a remainder, it's the same thing as if you factored in the solution for that binomial. Let's keep going. One more. Determine if x minus 3 is a factor of h of x equals x cubed plus 2x minus 3. So just for the sake of switching things up, I'm going to use long division. X cubed plus 0x squared plus 2x minus 3. So x fits into x cubed, x squared times, so I get x squared minus, x cubed minus 3x squared. I'm subtracting the whole thing, so I get a positive 3x squared. X divides, and I got to bring down my 2x. X divides into 3x squared 3x times. So I get 3x squared minus 9x, subtracting, so that becomes 11x minus 3. So 11 will go into, x will go into 11x 11 times, and I get 11x minus 33, subtract, and I get a remainder of 30. So make a prediction here. What do you think we're going to get when we plug 3 in, okay, for this particular polynomial? Let's try it. F of 3 equals 3 cubed plus 2 times 3 minus 3. 3 cubed is 27 plus 6 minus 3. 33 minus 3 is 30. Okay, so this is leading us to the remainder theorem, which is right here. That if I divide this function by this binomial, okay, so just think x minus 2 equals 0, x equals 2, that's what I plug in here. That's going to be my remainder. So this one I divided by x plus 1, that'll equal 0 at negative 1, but there's a remainder. This will equal 0 at 3, here's the remainder here. That's what you get when you plug in for 3. So if you divide a polynomial function by x minus a, so in this case, a equals 2. In this case, a equals negative 1 because it's x minus a, so you guys flip the sign. In this case, a equals 3. Okay. Then p of a is the remainder. So if you plug in whatever that a value is, it's going to give you your remainder. So in this case, a was 2. I plug it in, I get a remainder of 24. In this case, a is negative 1. Plug it in, I get a remainder of negative 2. In this case, my a was 3. I plugged it in, I got a remainder of 30. So your function, your polynomial function, is the quotient of x, okay, times x minus a, so there's the quotient that we got when we divided, times our divisor, x minus 3, okay, plus the remainder. If a number is a solution, or if it's a zero of that polynomial, there will be no remainder. That's really important to know. Okay, let's move on to page 3 of the notes. So it says, consider the polynomial p of x equals x to the 4th plus 3x cubed minus 36x plus 144. Question is 1 a zero of the polynomial p? Well, if it is a zero, then when we plug 1 in, it should cancel out. We should end up with 0. So let's plug it in. P of 1 is 1 to the 4th plus 3 times 1 cubed minus 28 times 1 squared minus 36 times 1 plus 144. And I'm going to get 1 plus 3 minus 28 minus 36 plus 144, and I get 84, which does not equal 0. So p of 1 is not a 0. Is x plus 3 one of the factors of p? Well, if x plus 3 is a factor, then that would be 0 at negative 3. So let's find p of negative 3. So all we do is we go back to the original equation and we plug in negative 3 wherever we see the p. Okay, and I'm going to get 81 minus 252 plus 108 plus 144. When you add all that up, you get 0, so yes, it is a 0. Now, let's look at the graph. The graph of this polynomial function that we're talking about right here, it asks what are the zeros? Well, I've got a 0 at negative 6. I have a 0 at negative 3. Ooh, I found that out already. I have a 0 at 2, and I have a 0 at 4. I did not have a 0 at 1, and I knew that already. Okay, so when you look at 1, it's right there. It's not a 0. So where are the zeros? Negative 6, negative 3, 2, and 4. So to write the equation, p of x equals x plus 6, that zeroes out at negative 6, x plus 3, x minus 2, x minus 4. Okay, moving on. This is the last part of this video, and then there's going to be a part 2. So not all polynomials have this nice coefficient of 1 in front of them. Sometimes they have a constant value in front of the polynomial. So it says to consider the graph of a degree 5 polynomial function shown to the right with x-intercepts at negative 4, negative 2, 1, 3, and 5. Write a formula for a possible polynomial function that the graph represents using c as the constant factor. So you just put the letter c out in front. So in the real world, most polynomials have some weird coefficient in front of them. So in this case, we don't know what it is yet, but f of x equals some number times, and let's look at where our zeros are. This one would be x plus 4, because at negative 4 it zeroes out. For negative 2, it's x plus 2, x minus 1, x minus 3, and x minus 5. Question B, suppose the y-intercept is negative 4. Find the value of c so that the graph of p has a y-intercept of negative 4. So the hint is the value of x at the y-intercept is 0. So if we say negative 4 equals c times 0 plus 4, so everywhere I have x, I'm just inserting 0 in there. It should be a 2. So I get negative 4 equals c times 4 times 2 times negative 1 times negative 3 times negative 5. So negative 4 equals c times negative 120. Okay, so to solve for c, we divide both sides by negative 120. So c equals 4 over 120, which equals 1/30th. So that is the number that actually goes in front of that equation. And if you were to plug that equation into decimals, 1 over 30 times x plus 4 times x plus 2 times x minus 1 times x minus 3 times x minus 5, and graph it, it would look just like that. Okay, we're done for now.